Okay, so this is where we stood in the last video is we're using standard candles, supernova type 1 that always have the same absolute luminosity, so we can use that as a distance, as a distance measurement. And the other thing that I was just getting, or I was about to say, is, this is actually really important, almost as important as having this distance ladder, is the fact that that there's overlap, and there has to be, right? There has to be overlap between each of these rungs on the ladder, right? Because you have to be able to use stellar parallax, right, to verify the next rung in the ladder, which is spectroscopic parallax. If there's got to be some stars that are close enough that you can actually measure using stellar parallax, and then of course you can always, with those you can always use spectroscopic parallax. And again, there should be some stars, some variable stars, some RR Lyra or Cepheid variables that are close enough that we can actually do stellar parallax, and then we can verify the distance. How much agreement is there between a Cepheid that is close enough to measure the distance using stellar parallax, and then using another method, right? So the variable, the actual Cepheid variable method. Okay, so in other words, you look at the stars period, and from the period you figure out what the absolute luminosity is, and then measure that. Use the inverse square law, and that'll give you the distance. So how well does that agree for a Cepheid? In that range, just using that method, and then and also that, let's say that same Cepheid is close enough for us to measure directly measure its stellar parallax, right? If the stellar parallax and the variable star method both agree, then you have confidence in the next rung on the ladder. All right. Now, Tully Fisher, you can't use the stellar parallax for Tully Fisher, but you can use the Cepheid method to measure individual Cepheids within spiral galaxies. The ones that are close enough that you can actually measure the. So close by ones, you can do this, and so you get some understanding of how reliable the Tully Fisher method is from finding variable stars and using that method, right, to measure the distance, and then using the Tully Fisher method to measure the distance. So again, you're checking your work using previous methods. So this is the overlap that I'm talking about. And then of course standard candles, right? I mean, you can use a standard candle. That works with any type 1 supernova, right? That can happen in a nearby galaxy, and if we if that's something that we've already used, the Tully Fisher method for that galaxy, then we can use the standard candle method to find out the distance of that galaxy. Also, if that galaxy is close enough, and we can see Cepheid variables, then we can use that method to find the distance. So again, you can actually you can use this overlap to check yourself, all right, or to check the work, which is really important in astronomy, right? You have to be able to verify that these things, that there is some overlap, and it gives you confidence in the next ladder. All right, so the next thing is to using these distance ladders, these various methods of finding distances. Where are we in the where's the Milky Way in relationship to other galaxies, for example? So we exist in the Milky Way. It exists in what's called the local group. I know it's a really advanced name, right? The local group of galaxies. And this is about roughly 50 galaxies, so it's a distance of about one megaparsec. All right, so you go out from where we are about 1 million parsecs outward, and you're going to pick up all the galaxies within the local group. And so there's actually just 3 large galaxies here. So let's see. The 3, of course, are Andromeda, which is a large. It's actually larger than the Milky Way, about twice as large as the Milky Way. The Milky Way galaxy, and of course M31. I'm sorry. So M31 is Andromeda, and also M33, which is also a spiral galaxy. Sometimes that galaxy is called Triangulum, just to let you know that it's not that important. But most of the members, so those are the 3 big ones, and again, they happen to be spiral galaxies. The other ones in this local group are usually tiny galaxies, both irregular and dwarf ellipticals, and they, like for example, the 2 irregular galaxies that orbit our galaxy, the large and small clouds of Magellan. Those are just a couple of examples. The vast majority of the members of the local group are these tiny little galaxies, both irregular and dwarf ellipticals. Now, the thing about the distinction between what's called a group of galaxies and a cluster of galaxies. So our local group would be considered a kind of a weak cluster, like weak in the following sense. Most of the clusters of galaxies that we see have really large, at least one large elliptical galaxies. One of these really large ones. Well, it doesn't have to have it doesn't have to be like one of the exceptionally large ones, but there's usually at least one or more large elliptical galaxy, and so that's generally called a cluster of galaxies. There just doesn't happen to be one in our local group, and so here's a nearby cluster of galaxies, called the Virgo cluster. So the Virgo cluster has roughly. So remember, our local group had maybe 50 galaxies or so, with just 3 of them that are large galaxies. So this Virgo cluster, and again, this is a relatively nearby cluster, has about 3,500 galaxies, and there are large elliptical galaxies. There's spiral galaxies. There's all sorts of stuff in the Virgo cluster, and of course there's other. Here's another cluster of galaxies. This one's is about 1 billion parsecs away. All right. So that's, and then there's many other clusters out there. There's the Hercules cluster. I mean, a lot of them are just named for what constellation they're in. Some of them have a little bit more interesting names that reflect like the person that just first discovered that cluster. All right. So now here's something that and this is going to extend. Recall, we've got our distance ladder, right? So we're up here with standard candles using type 1 supernova. What's the next rung, or really the final rung on our distance ladder? All right. So this is the first steps towards that. All right, so here's this is something that Hubble discovered in the 1920s, all right? When he looked out at other galaxies, and in fact, remember, Hubble's the first one to find other galaxies, the fact that other galaxies existed. And in fact, he used Andromeda, and he used Cepheid variables in Andromeda, in the Andromeda galaxy. Remember, that's the large nearby galaxy. It's about 2.5 million light years away. Anyhow, he was the first one to ever using Cepheid variables to find the distance to another galaxy. And he really, nobody. I mean, we saw astronomers had seen what turned out to be other galaxies in their telescopes, but they didn't know they were other galaxies. They just called them nebulae or nebula. And so when Hubble using the method of the Cepheid variable, right, using variable stars, he found the distance to Andromeda. All right. So here's another thing that he discovered, and this has become known as Hubble's law. So now there are just a handful of exceptions, like for example Andromeda, right? Andromeda doesn't follow this, just because Andromeda is relatively close. So this is true for the vast, like all the galaxies, except for just a couple of galaxies that happen to be really close to us. All right, and so this is what's called the recession velocity. All right. So now what Hubble did is he looked at the galaxies themselves, and he found that there was a redshift. Every single galaxy seemed to have a redshift, and the further away the galaxies were, the more the redshift. And in fact, there was a relationship between the amount of redshift. So remember, what we're talking about is generally is hydrogen lines. Let's see, did they show us that? No. They're showing us right here. So the absorption lines for hydrogen, I mean, we can identify those really easily, and when we do that, we can tell how much the light has shifted towards the red end of the spectrum. So again, this is with every galaxy except for just a couple that happen to be really close to us, like Andromeda and Triangulum. So what this is and this is the discovery that he made, and again, this is certainly Nobel Prize winning stuff. He didn't win a Nobel Prize for it. I'm not really sure why, but certainly if this was done in more modern times, he would have won a Nobel Prize. I think it probably because he passed away. It turns out, like, when you win a Nobel Prize, you have to still be alive to win it. They don't award it posthumously, unfortunately. Anyhow, what he discovered, and this is actually some of the information from his original. Let me get my mouse here. His original work. He found that there seemed to be a linear relationship, and then when he looked out at further, more galaxies, he found that there was this linear relationship. That is, there's a relationship between the redshift and the distance to the galaxy. So the greater the redshift, right? So like let's take this one right here. So let's say you get this. So the redshift will give you what's called the recession velocity, right? It's just right from the Doppler effect. That's where you get this, and so that tells you how far away it is, and that is called Hubble's law. Right? The recession velocity is equal to a constant now called Hubble's constant times the distance, And so Hubble's constant is in units of, so this is the one that